Good morning, everyone, from my side as well. I am Thomas Christou, and I will show you my part in this Magister project, which involves the experimental investigation, as the title suggests, of the pre-filming air blast atomization process under periodically oscillating airflows. So, as we know, the air transportation in the past decades keeps growing, so we tend to find new cleaner combustion technologies, the aviation industry. One of the proposed concepts is the lean premixed prevaporized combustion operating at higher pressures, which may have a positive impact on the reduction of the emissions, but on the other side, it introduces thermoacoustics in the system, and I think we all know the destructive potential that they may carry for the hardware of the engine. So in the thermoacoustic cycle, what I'm most interested in is the inlet air velocity, which becomes heavily unsteady through the feedback loop from the unsteady heat release. So the inlet air velocity strongly affects the air blast atomization process because most of the modern jet engines employ air blast atomizers for the disintegration of the liquid fuel. So if the inlet air velocity undergoes strongly periodic oscillations, then the air blast atomization process changes, and we need to know how it changes because it also affects the emissions themselves and the flame stability and even the color of the flame, the soot emissions, and so on. So in this presentation, we will see a very brief theory about the air blast atomization process, the setup, the experimental setup for design and build for these research activities, the measurement techniques that I have set up and used to carry out this work, the results, the main outcomes, and finally the publications from this work and a brief summary. So the air blast atomizer and the pre-filming air blast atomization process in general, the principle is quite simple. A liquid is injected on a flat pre-filming surface, creating a thin liquid film, at the end of which, through the help of the air stream coming from above and below, as you see in the photographs, the liquid film is sheared, and at the end of at the edge, it is disintegrated in a spray of droplets, a spray of fine droplets. So one of the characteristics measures of the spray is the Sauter mean diameter, which denotes the volume to surface area ratio of a single droplet that has the same volume to surface area ratio of the whole spray. So it's a characteristic measure. We will come back to that later in the results, of course. It is strongly dependent on the airflow, and that's why we expect it to change. It decreases with increased air to liquid ratio or with increased pressure drop across the nozzle. So moving to the experimental setup, the operation is quite straightforward. The air is supplied in the system by a compressor, which is then split into branches. One part of the airflow passes through a siren, a pulsating device, which generates the oscillations in the flow, while the other part is bypassed from the siren through an air plenum. You can see in this photograph a sketch of the siren and the plenum surrounding it. And the two flows coming at the exit of the siren and the plenum, as you can see through these holes here, they coaxially mix at a long resonance tube, which is, of course, in a cross-section in this photo for illustration purposes. And at the end of this resonance tube, we have placed an air blast atomizer, in this case a model atomizer, a model pre-filmer, where liquid is directly supplied through a pressurized vessel. The liquid in this case is water. Of course, at the end, the water is collected in a tank and the excess air is being sucked through a vacuum pump to avoid unwanted recirculations in the measurement region. So some practical operating conditions for the test rig. I am operating at atmospheric pressures with pressure drops across the nozzle in the range of 1 to 4%. Usually I'm at 3%. Air to liquid ratios can actually vary. We can go up to 200 maybe, but usually, of course, I operate at quite lower. We will see that in the results. And excitation frequencies can go theoretically up to 800 Hz with the current setup. In the context of the thermoacoustics, it's more interesting up to 500 Hz maybe. Now, moving to the measurement techniques, we have set up and employed those three: hot wire constant temperature anemometry, shadowgraphy, and phase Doppler anemometry. So with hot wire, as you can see, it is mostly suitable for airflow measurements. It measures the velocity of the air. And since we are able to achieve relatively high data rates, even 40 kilohertz, for example, in this case, it is suitable for characterizing a forced airflow, a highly oscillating airflow. On the other hand, shadowgraphy is a low-frequency technique, so it is mostly suitable for non-forced experiments in order to characterize the prefilmer's performance. And of course, it measures droplets' size and velocity, not the air. Finally, the phase Doppler anemometry also measures a droplet flow, the droplet size and velocity. And depending on how dense the spray is, data rates of approximately 10 kilohertz can be achieved, which makes it suitable also for forced experiments with the oscillation, but of course also for steady experiments without oscillation of the flow. So, starting with some results from the shadowgraphy technique in non-forced conditions without the use of the siren yet, we are measuring in this region, the spray region, some millimeters downstream of the atomization edge, as you see, from 10 to 45 approximately, in a pressure drop of 3% across the nozzle and air-to-liquid ratio of 26. And you can see in these graphs the droplet velocity, the outer mean diameter, and the number density actually, which depends on the grid of this graph. Important is to notice the trend along, first of all, the z-axis, moving downstream from the atomization edge, and we see that the velocity increases, which makes sense since the droplets have more space in order to accelerate. And of course, if we move from the center line radially in the x direction, which you can see here, we see that the velocity increases up to a local maximum at -5 or 5, and then decreases again going at the edge of the spray. This we will also see later in some other results, so keep it in mind. The outer mean diameter, on the other hand, as well as the number density, is higher at the center line, and moving radially, it drops and then is quite stable after some millimeters, from 2 or 3 millimeters to 10. The number density, of course, denotes how dense the spray is in the center and how it spreads to the sides, with where we have lower droplets, and of course smaller data rate can be achieved. Moving on to the PDA results again for non-forced cases, we can see that having measured a plane where on a surface which is perpendicular to the flow direction, the XY plane, which you can see here at a downstream distance of 40 millimeters, the same operating conditions as before, and we can see on the top right graph the trend of the mean velocity and the outer mean diameter measured with PDA. So you can see first of all that the velocity going from 0 to -10 follows exactly the same trend as the shadowgraphy showed. It first increases a local maximum at around -5 and then decreases again, and the outer mean diameter again the same trend, starting with a local maximum at 0 and then dropping and staying rather constant until the edge of the spray. Now, finally, through a computational algorithm, we're able to calculate the mass flux from each of the 60 measured positions in this plane. And this is actually what you see in the bottom right graph, where we have all the measured and calculated mass fluxes through the PDA collected data in the XY plane. And you can see actually the density of the spray as we saw before. Near the center line, the density is higher, and moving to the sides, the density, the spray mass flux is almost 0 at -10 and +10. And of course, since this covers almost the whole range of the spray in this cross-sectional area, by integrating the volume under this surface, we are able to calculate the mass flow rate in kilograms per second or kilograms per hour, which in this case is very close to the actual mass flow rate that we were supplying the system, with a deviation of less than 8 or 9%, which is important because we will use the same algorithm to calculate the mass flux afterwards in the oscillating case. So we are able to trust it. Now, before moving to the actual results of the PDA in the forest flow, where you can see the analysis at the radial distance, x was made, we first have to characterize the airflow, because we need to see how the siren operates, what kind of fluctuation it creates in the flow. So by measuring with the hot wire a variation of excitation frequencies in the range around 120 Hz for this presentation, we can see that this is the fast Fourier transform of all those measured cases, and each of these peaks denotes the amplitude of the fluctuation for each of the measured excitation frequencies. So for this presentation, I have chosen to show you the 120 Hz for a number of reasons. So all the results that you're going to see from this point are at this excitation frequency. Of course, you can see directly the phase averaged air velocity here, measured and calculated through the hot wire in one cycle of the phenomenon. So, of course, the pressure drop will vary, so an average of 3% was expected, and air-to-liquid ratio, average air-to-liquid ratio 26. So, from now on, most of the graphs regard the position x equals 0, and at the end we will see what happens to the other radial distances. So, at a glance, we can see that most of the measured droplet characteristics undergo a strong oscillation in between this one period of the phenomenon. You see in the x-axis the phase angle, which denotes the period of the phenomenon. This is a repeating behavior. So let's start with the mean diameter, the black curve here, which we see it undergoes a strong influence because of the excitation of the airflow, and also the number of the droplets that cross the measurement volume of PDA is unsteady. In a steady case, without using the siren, of course, the mean diameter would be quite constant in time, and of course also the number of droplets would not have such a strong deviation in time. On the second graph, we see the raw data of the droplet diameters collected through the PDA technique, and on top of those, we see the two graphs denoting the mean diameter, which is the same graph, the same curve that we saw on the left graph, and the outer mean diameter, which, as we see, follows exactly the same trend as the mean diameter, of course. So each dot that you see on this graph is a single droplet of the total samples measured for this experiment. And in color, you see the number density in this graph, because of course in this region, since the dots are so many, this helps visualize the number of droplets in each phase angle. And we see that this trend here in the color matches the droplet number, where a peak at around 270 degrees is noticed. So the same graph with the raw data can be seen also for the velocities of the droplets, where we see the phase averaged mean droplet velocity in a black curve by phase averaging the raw data, dividing all the period in 20 subsections. So you see the 20 points. And of course, also the color denotes again the number density. So you can see that, for example, in this region again, it's more red, like here. So we know that it was mostly small droplets that appeared in this peak of number, but these small droplets have a variation of velocities. They have a wide range of velocities. Now, to see exactly what velocities have each diameter sizes, we can calculate again a phase average droplet velocity by taking into account only diameters of a specific diameter class. So starting from the first curve, which denotes all the droplets from 0 to 10 micrometers, then 10 to 20 micrometers, and so on, until the final one, which is 160 and higher, we can see, first of all, that the obvious, the smaller the diameter, the higher the average velocity, due to their inertia and their low Stokes number. And also, as the diameter gets higher, not only the average velocity is lower, but also the amplitude of the oscillation is smaller. And after some point, I would say after 100, 110 micrometers, we see that the curves pretty much collide one on top of the other, they stack. So this is the minimum border, the minimum velocity, which matches pretty much the edge of the raw data that we actually have here. So moving to the Sauter mean diameter, as we saw briefly before, it again undergoes a strong oscillation, exactly like the mean diameter. But interesting here is to notice the average of this curve. It's this dashed black line. Now, if we were to compare the average SMD in a forced case with the SMD of a steady case without oscillation, where the airflow has a velocity which is the average velocity of the oscillating case, then we would see that the two SMDs are quite close, and the SMD of the forced case is slightly higher than the SMD of the average velocity in a steady case. Now, this can be also explained numerically by using a computation for the SMD, a model from Geppert. And we can see that this model, because each of the terms in this model is dependent on the gas velocity, ug, the air velocity, we can simplify this equation in the second one, where c is just a constant of all the constants of liquid and gas and the geometry, of course, of the system. And then the Sauter mean diameter can be directly correlated to the gas velocity. So inserting in this equation the measured air velocity through hot wire, which is oscillating, this one in this case, the air velocity, we can calculate an oscillating Sauter mean diameter, which is the black curve that you can see. As you can notice, it has a strong resemblance with the actually measured Sauter mean diameter. And of course, you can see that the average of that forced SMD is almost the same as the SMD of the average velocity calculated again through this equation. And again, the SMD, the average SMD is slightly higher than the SMD of the average velocity. So finally, we can see the mass flux of the spray calculated again through the formula that I showed you before in the steady case, which again undergoes a strong oscillation, which we know would certainly affect the air-to-liquid ratio, which is calculated using the air velocity measured through the hot wire. And we see that indeed it also undergoes a strong oscillation. In this graph, you can also notice a fraction of the global air-to-liquid ratio, 4/7 fraction of the global air-to-liquid ratio, which makes sense in this case, since in the pre-filmer, the water is flowing through these holes, creating a thin film of 40 millimeters, while the air is flowing through the whole duct of 70 millimeters. So just for a more fair comparison in a local air-to-liquid, with the local air-to-liquid ratio, it would be more fair to take this specific fraction of the GALR. And it turns out that it is also pretty much in the range of the fluctuation of the local ALR in this position. So finally, the analysis of the same parameters in the radial direction, in the x direction, you can see that it has a very similar behavior to the non-forced conditions. As you remember this graph, moving from 0 to -10, the velocity increases with a local maximum and then decreases again, and the SMD has a local maximum at 0 and then decreases and stays rather constant. Of course, both of them have a strong periodic oscillation in all of the different radial positions. And to finalize with this, we can see the calculation of the oscillation amplitude of all the main droplet characteristics This amplitude is a percentage relative to the average value of each of those characteristics. So we see that the droplet velocity has an oscillation of approximately 15%, 15% relative to its average value, the SMD around 20, and we see that the spray mass flux is around 30 to 40% over its average, and the ALR even higher, 40 to 50% over its average, which of course you can understand is makes the combustion very unstable. Finally, the publications from these research activities, we have already made one in the Automation and Sprays journal, one on the this year's actually ASME Turbo Expo, which has been accepted recently, and the next one that we're targeting is the European Combustion Meeting of this year. So, to summarize what we saw in this work, the design and setup of an experimental spray test facility in order to measure the spray characteristics under forcing airflow. The setup of 3 measurement techniques in order to characterize either the airflow with hot wire or the spray and the spray characterization in forced and non-forced conditions through shadowgraphy and PDA. And finally, the ongoing activities. We are making a frequency variation right now at 100, 200, approximately 300 and 400 Hertz to make a comparison and how the same result change, a systematic variation, the influence of the air to liquid ratio for any determined frequency, and the characterization of another burner design in cooperation with the University of Twente. So, thank you very much. I'm open for your questions.
Okay, thank you, Thomas.
Thank you so much.
For your very interesting presentation.